problem 12 in the document for today gives you an example of a slinky, 23 meters long, a long slinky, 60, almost over 70 feet long, under tension of 17 newtons, not a whole lot of tension, and that slinky's probably going to be dragging the ground with that little bit of tension, but let's say we've got some means of levitating it and still maintaining the tension. And total mass of 0.9 kilograms, a couple of pounds, okay? Well, there's more to it. I'm asking you about harmonics and frequencies and so forth, but at this point we would automatically stop, I would hope, and calculate the propagation speed of the wave in that slinky. And it's going to be square root of tension over mass per unit length. Here's your mass, here's your unit length, or here's your length, and it comes out about 21 meters per second, and you can verify that. That's not going to give you any trouble. So here's a picture of the slinky. It's fixed at both ends. It's 23 meters long. Now the question is, what are frequencies of the first three harmonics that you would get in this slinky? Okay, in other words, what are the frequencies of the first three oscillations? The one with the longest wavelength, the one with the next longest, and the one with the next longest. Well, the slinky can oscillate this way. That's going to have nodes at both ends, so that's just your node, antinode, node configuration, in which the wavelength, the length of the slinky is 2/4 of the wavelength. Okay, 2 quarter wavelengths. Here's a quarter wavelength from node to antinode, and from antinode to node. There's another quarter wavelength. So we can have 2/4 of lambda equals L. And if that's the case, we're going to call that wavelength lambda sub 0. That's called the fundamental. Okay? Or we could have 4 quarter wavelengths in here. We know that if there are nodes at both ends from the pictures that we saw just a minute ago in the last video, we can have nodes at both ends. And we could have an antinode, then a node, then an antinode, and a node. In other words, our wave could look like this as it goes back and forth. That corresponds to node, antinode, node, antinode, node. And that is a behavior that comes out of the picture that we get from reflecting waves, if the length is just right. Okay? So we get that. So we get lambda 1 would equal L, because there are 4 quarter wavelengths there. 1, 2, 3, 4. 4 quarter wavelengths equals L, so lambda 1 equals L. Or we could have 6 quarter wavelengths. I'll draw that one within this one. So let's see, we're going to have this. No, I'm getting the wrong one. Okay, did it wrong. We have this, and then we're down here, and then we're up here, and then we're here. Okay, I wasn't thinking very clearly when I did that, but right there is the configuration you would have for the second harmonic. 6/4 of lambda 2 equals L, so lambda 2 is 2/3 L. So we have F0, our fundamental frequency. Well, wavelength frequency. Frequency is propagation speed divided by wavelength, and that's something that I assume you have well established by now. We've been talking about that for a couple of weeks, or at least a week and a half. So there's our fundamental frequency. Here's our first harmonic, C over L, wavelength being L. Here it's C over 2/3 L, which is going to be 3/2 C over L. So we have what? 1/2 C over L. We have 1 times C over L. 3/2 C over L. What's next? The obvious progression, and the progression that you would get if you analyzed it in terms of the previous picture would be 4/2 C over L, 5/2 C over L, etc. And you could say the frequency of the nth wavelength is C over the nth wavelength itself, and that's going to be n plus 1 over 2 times C over L. If n is 2, you got a 3 here. If n is 1, you have a 2 here, 2 over 2. If n is 0, you have just a 1/2. So there's your relationship. You can reason this out. If you try to do this by memorizing a bunch of meaningless formulas, you're never going to get it right, unless you happen to have a photographic memory. You won't keep those formulas straight. Those formulas mean something, and the meaning of those formulas comes from our pictures, and it's not a difficult picture. So I strongly advocate that. We could do the same for the wavelength, for the nth wavelength, and see how that's related to this. And that's all something you should work out for yourself. I've already suggested that you work out the next few wavelengths and maybe get this relationship. And you can do the same thing with frequencies.